This recording is going to cover the respiratory as well as the renal compensation for acid-base imbalance. First one we're going to do is covers respiratory compensation. So what is it? How does it play a role in regulating pH by changing ventilation rate? Well, respiratory compensation is affected by two different types of receptors that we have. We have the central chemoreceptors located in the medulla oblongata. They're monitoring carbon dioxide levels. Actually, it's elevated levels of carbon dioxide in the blood that can cross the blood-brain barrier. And remember that it will, within the cerebral spinal fluid, will create hydrogen ions which actually bind to the central chemoreceptors and will increase ventilation rate. But it's the response was to elevated CO2 levels in the blood. The carotid and the aortic chemoreceptors, they sense changes in oxygen levels and CO2 levels in the blood. But the carotid chemoreceptors, I have to correct this picture, is carotid bodies are the only chemoreceptors that respond to elevated levels of hydrogen ions in the blood. The aortic do not, but aortic chemoreceptors will respond if you've got elevated carbon dioxide levels. One of the things that you'll see is by law of mass action, what can happen is, because of the law of mass action, if you have elevated hydrogen ions in the blood, that combined with bicarbonate form carbonic acid, and then that dissociates into CO2 plus bicarb. So indirectly, because of the law of mass action, if you have elevated levels of hydrogen ions in the blood, that could lead to more CO2. Then that will set off the central chemoreceptors because the CO2 can then cross the blood-brain barrier. But what we have is, if you've got metabolic acidosis, you will increase ventilation. And when you do that, that helps to decrease this carbon dioxide. And again, by law of mass action, we're going this way, that will help to decrease hydrogen ions. If you've got metabolic alkalosis, the respiratory compensation is going to be a decrease in ventilation. So respiratory compensation only applies if with metabolic acid-base disorders. Respiratory compensation cannot occur for acid-base disorders because of the primary defect is respiration. So this picture is going to kind of show you similar thing we're showing you with changes in ventilation, but it's also going to kind of give you just really broad what you'd expect to see with renal compensation. So let's just look at, so I have added hydrogen ions because of producing, say, more lactic acid. Well, with this one, what we see is you're seeing at least one of the buffer systems is, you can use the bicarbonate buffer system, is the hydrogen ions combined with bicarb, and you follow the red arrows, we're going in this direction here, and CO2 can be expelled by increasing respiratory rate. So that could be a response to a acid-base disorder, and specifically metabolic acidosis. At the same time, it's not as quick to act, but at the same time, in the kidneys, just think logically, what do you want to happen? I have all this excess hydrogen ions, that's going to cause my pH to drop. I don't want that. I got to get rid of them. So you want to increase the excretion of hydrogen ions, and you want to conserve bicarb, because that's going to help with my bicarbonate reserve. So it helps me with this kind of buffering up some hydrogen ions. However, if you have, say, removed hydrogen ions, so you look at the blue lines, So I've been thrown up a lot. I've lost a lot of my stomach acid contents. Is what you'll notice with that, I'm going to, let's erase this. With this, I'm going in this direction here is carbon dioxide, which I'm always generating anyway. I'm going to combine with water, forms carbonic acid, that dissociates into hydrogen ions, and that's going to allow me to add more hydrogen ions because I've lost some, and then you've got your bicarb. Well, at the level of the kidneys, I'm going to excrete that bicarb. I'm going to conserve hydrogen ions, so I'm not going to be secreting hydrogen ions. I'm going to conserve them as much as possible. And also at the same time, which contributes to what you see here, is my respiratory rate is depressed. So just think logically what you want, and most of it you'll understand. You'll be able to answer most of the questions. So just think logically, what do you want to happen? So let's look a little bit more in depth at the renal compensation, because it's obviously not as easy as you see here. So let's look at the renal compensation for acid-base disorders. So in the early parts of your nephron, your proximal tubule, your thick ascending limb of the loop of Henle, and the early distal tubule. This does not apply to the descending limb of the loop of Henle or the thin ascending limb. But most of this right here that you see here does take place in your proximal tubule. Is what you see here is showing you that's typically could happen is you're going to have secretion of hydrogen ions by secondary active transport. And so here you see hydrogen ions being secreted in exchange for a sodium. So the sodium reabsorption is driven by this sodium potassium pump that's located over here. So over here you have this sodium hydrogen exchange protein, and what you're noticing is this is an example of where we see an antiporter. So hydrogen ions are being secreted into the tubular lumen in exchange for sodium. Well, what the hydrogen ions being secreted is specifically to allow us to reabsorb a bicarbonate. And so bicarbonate that's been filtered in the kidneys, we're going to bind to that hydrogen ion that was secreted, forming carbonic acid. And actually, it doesn't really show it very well in here, but what this reaction is actually taking place within the brush border of the proximal tubule, not in the lumen itself. And then the carbonic acid dissociates into carbon dioxide and water. So this is happening really in the tubular cells. And so you have CO2 and water here. Then that again just dissociates back again into carbonic acid. Then that dissociates into hydrogen ion, which is then secreted. And the bicarb is going to be reabsorbed. We'll have a protein allow us to reabsorb it here. So really, that secretion of the hydrogen ion was really needed just to absorb or reabsorb a bicarbonate. We don't have really a lot of any net secretion of hydrogen ions. Now, if we think about what could happen with certain metabolic or respiratory acid-base disorders, if I've got increased carbon dioxide in my blood, you see like here, if this starts to increase because I have, say, respiratory acidosis, got a problem, say, with gas exchange. You'll see this is, elevated CO2. It's readily can cross cell membranes. We're going to be going here. Law of mass action again. This is going to go into the tubular fluid cell. You see this reaction going on here. And what's going to happen is I'll secrete this hydrogen ion. And what's going to happen is if I've got that respiratory acidosis is I want to conserve bicarb though, because that will help to prevent some drastic changes, and I want to secrete the hydrogen ions. And so you're going to secrete the hydrogen ion, and you'll be able to reabsorb some bicarb. Now, if I have metabolic acidosis, the hydrogen ions combine with bicarb in your blood, and that dissociates into the carbonic acid, and then that dissociates in CO2 and water. What's going to happen is you're going to have less bicarbonate that's being filtered because it's being tied up in your blood. So with less of this being filtered, you'll get a little bit more hydrogen ions that'll be increased in the tubular fluid. Say if I'm tying up all my bicarb, I'm not going to actually be reabsorbing it. If it's going to be already be tied up, you'll get more hydrogen ions being secreted. But unfortunately, you can't secrete a huge amount of them. I need a little bit later on to get rid of a lot more hydrogen ions. Now, if we use the scenario, if you've got, say, alkalosis, with respiratory alkalosis, you're going to have less CO2. So that leads to less hydrogen ions being secreted. And that would favor the excretion of this bicarb, because I'm not going to be able to reabsorb it. And that's what you want to do, is get rid of any excess bicarb. If you've got metabolic alkalosis, you're going to have more bicarbonates going to be filtered. And if you have less hydrogen ions that are be secreted, you're going to end up with not going to be able to absorb as much. You're going to have more excretion of bicarb. So it just kind of think about it, is if I'm acidotic, I'm going to have less bicarb being excreted. If I'm alkalotic, I'm going to have more bicarbonate excreted. Now, where the more hydrogen ions being excreted or not, or secreted, I should say, are real important later on in the nephron tubule. So we have intercalated cells in the late distal tubule and in the cortical collecting tubule. And we actually have two types of intercalated cells. If you're acidotic, the type A intercalated cell is going to be responsible for this really increased secretion of hydrogen ions. And hydrogen ions are going to be transported into the tubular lumen by primary active transport. So you have a hydrogen ATPase located there. And so you're going to be pumping out these hydrogen ions, and it can increase quite a bit. And the reason why it can increase quite a bit is because we're going to have to use urinary buffer systems to do it. We have a phosphate buffer system, and we have what we call an ammonium buffer system. And I want to show you. So here's just kind of showing you the phosphate buffer system. So you have the hydrogen being secreted here, and it combines with the monohydrogen phosphate to form dihydrogen phosphate that kind of traps that in the tubular lumen, and we'll be able to get rid of that excess hydrogen ion. Having a buffer system actually makes it a lot easier to be able to secrete more and more hydrogen ions into that tubular lumen. Now, even more important buffer system than the phosphate buffer system in the urine is the ammonium buffer system. So here, this is kind of really generally kind of going over some of the things that are important in the use of this buffer system. In your kidneys, and it's going to be at the molecular level, so we're not really going to go into that, is if it senses that we're acidotic, it knows that we need to metabolize more glutamine, which is an amino acid. In the process of glutamine metabolism within the proximal tubular cells, what we end up forming is 2 bicarbonates and 2 ammonium ions. And ammonium, what it does is it actually formed ammonia, but ammonia, which is this, it's a base, combined with a hydrogen ion and you formed ammonium. And so ammonium is acting as a buffer component and tying up some hydrogen ions. And so in the process of the metabolism of glutamine, we have done 2 things. We have generated new bicarbonate because I need more bicarb because that will help to buffer any excess hydrogen ions around. 2, it's allowing me to get rid of more hydrogen ion. It's actually acting as a buffer. And I'm going to tie that hydrogen ion up and then allow me to get rid of it in the body. And it's technically, it's more complicated than this, but kind of like every step along the nephron tube or where it happens. But this buffer system is an extremely important buffer system in the kidneys. The here, this is showing you in what would happen in the collecting tubules. And so you'll see here's that hydrogen ATPase, and here's some ammonia, and the hydrogen ions combine with the ammonia, forming ammonium, and it traps it in that tubular lumen, and we're going to take it out. And so that buffer system is fairly important. You can increase the amount of hydrogen ions a significant level. So this buffer system is real important. So you can generate more bicarb and you can get rid of more hydrogen ions using this. Now if we go back to this picture, I want to show you that here, so we have, you're acidotic, you got hydrogen ions. That bicarbonate can act as a buffer. That combines with it, and they've skipped a step, but remember that it combines to form carbonic acid, but then you generate carbon dioxide and water. And so you see the carbon dioxide and water here. That Ca is carbonic anhydrase because that's an enzyme that catalyzes this reaction. That in the intercalated cell, you'll combine that to form, again, carbonic acid, but then that dissociates into hydrogen ion, which you see is going to be secreted using that proton pump, this hydrogen ATPase. And then you have the bicarb here, which then is exchanged for chloride, and that's going to act as a buffer there. Now, one of the things I want you just to just observe, in case you were interested, is as a result of what you're seeing here, we do tend to reabsorb more potassium. Acid-base imbalances can affect blood potassium levels too. So I just want you to be aware of that. So if someone's acidotic because of what you see going on here, that can cause hyperkalemia and vice versa. Now, if you have alkalosis, you'll see the activity of the type B intercalated cell. And in this scenario, you're seeing we're going to get excretion of more bicarbonate, and we're going to reabsorb hydrogen ions. So you have the hydrogen ATPase here. The hydrogen ions are going to go back into the blood. So it's just the opposite that you would see that would happen. And just think logically again, if you're alkalotic, let's get rid of bicarb. I don't want it. I want to retain as many hydrogen ions as I want. So it's just the opposite things that happen in a type B intercalated cell. And your body knows which cell needs to be active at that point in time. Just going to make this just as simple as that. Okay, so let's do a quick kind of recap of respiratory and renal compensation. So respiratory compensation, you have an increase in ventilation in response to a metabolic acidosis, because respiratory compensation does not apply for any respiratory acid-base disorder, because that's the primary dysfunction. You have decreased ventilation. In response to alkalosis. It'll be metabolic alkalosis. You have central chemoreceptors that are responding to changes of carbon dioxide levels in the blood, because that can readily cross the blood-brain barrier. And you also have the peripheral chemoreceptors that will affect ventilation. And the primary one is the carotid bodies, because that will monitor the concentration of hydrogen ions in the blood. So that can change ventilation there. Now the renal compensation. So renal compensation. So if you have, we'll say, acidosis, any reason whatsoever, this is what's going to happen in the kidneys. So in the kidneys, up at the proximal tubule, if you're acidotic, you're going to probably not be filtering as much bicarb because it's going to be tied up. You'll have increased hydrogen ion secretion / excretion. You will end up, and it's going to be more important in the latter part of in the intercalated cells. So you'll have the type A intercalated cells that will be working. And what we'll have is increased hydrogen ion secretion, excretion. You'll have increased reabsorption of bicarb. You'll have, and I'll say, and generation of bicarb, because you'll have an increased glutamine metabolism. Because that ammonia that's generated as a result combines with a hydrogen ion and you form ammonium ion. That allows us to really increase the amount of hydrogen ions that you can secrete there by those intercalated cells. The phosphate buffer system is also will play a role, but this one's the most important. So you have that phosphate buffer system. So this is if you have acidosis. So overall, if I was going to sample your urine, you're going to excrete a more acidic urine. Well, what about alkalosis? Well, I'm tired of writing, so I'm going to see if I can just change some arrows here. So if I'm alkalotic, so I'm going to do this, alkalosis. With alkalosis, you're not going to be secreting hydrogen ions as much, so you decrease it, and so you decrease the excretion of it. So you're going to have a more alkaline urine, and what's actually going to happen is decreased reabsorption, decreased reabsorption of bicarb, and you're going to have increased excretion of it. You're going to have decreased generation of bicarb. I don't want any more. I want to get rid of it. Decreased glutamine metabolism. This is not going to play a role. You're going to have not the type A intercalated cell that's more active in that late distal tubule and the cortical collecting tubule. The type B intercalated cell will be active, working, and you're going to have decreased secretion of hydrogen ions, and therefore less secretion or excretion of it. So it's just the opposite. Okay, I know I've tried to it's try to make it as simple as I can. This is a lot more complicated, so I just try to make it as simple as I possibly can. This is one of the hardest things to teach, I have to admit. So just try to keep it as simple as you possibly can. Like overall, what type of things are happening in the kidney as a result of being acidotic or alkalotic. Okay. The hardest things, just remember type A versus type B intercalated cell. To me, that's the one you just have to memorize that.